Good evening, everyone, or good morning, afternoon, insert appropriate greeting for your time zone, and welcome to this month's edition of Astronomy on Tap Edinburgh. Now, because this is the new normal, we're not actually coming to you from Edinburgh at all, and we have three excellent speakers lined up for you from three entirely different time zones. Because if there is one silver lining to this pandemic, it's that that's a thing we can do now. So I'm really excited to welcome our first speaker tonight, who is Dr. Jeffrey Silverman. Brief introduction to Jeff. Jeffrey Silverman is Director of Data Science and Analytics at Samba TV, where he uses big data to, among other things, figure out exactly how many people are watching Killing Eve. Before moving into the tech industry, Jeffrey was an NSF Astronomy and Astrophysics postdoctoral fellow at the University of Texas at Austin and earned his PhD in astrophysics at the University of California, Berkeley, working on observations of supernovae and dark energy with Professor Alex Filipinko. Jeffrey is also heavily involved in various science communication and public outreach programs, including co-hosting Big Screen Science, a weekly movie showing followed by a science presentation via Twitch, which is one of those young people things that I know nothing about. Now, I know Jeff from when we both worked together at the University of Texas at Austin, where we, among other things, co-founded Astronomy on Tap ATX. And I am representing, you can't really see, there's my Astronomy on Tap ATX t-shirt, the OG t-shirt. Are you wearing it too? Oh, fantastic. Also got my cider. This is from a cidery that Jeff and I visited last time he was in England in my, oh, you can't really see, virtual backgrounds. They're a nightmare, aren't they? Same distance as me, does that work? There you go, Astronomy on Tap ATX glass. You guys need to send me an Astronomy on Tap Edinburgh glass and then I'll represent you. So how are you doing tonight, Jeff?
I mean, I'm doing well this morning since I'm in California where it's 11:30 in the morning. So in honor of that, I have a California breakfast beer made with coffee. So, you know, starting off the day all right.
Breakfast beer. Today I learned that's a thing. So Jeff is going to talk to us tonight about stars that go bang and how this is solving one of the biggest mysteries in the universe. Have I just made you feel really big and clever and important with all those big words there?
I mean, my hair makes me feel big and important, but that's beside the point. I'm rocking the shelter-in-place quarantine fluffy hair, so.
Oh, I got my hair done for the first time in like 5 months last week. It was beautiful.
Excellent.
All right, well, over to you, Jeff.
All right, so I will share the screen and we will get going here. All right, thanks Rachael, thanks everybody at AoT Edinburgh. I have never visited Edinburgh. I've heard it's beautiful. I would love to get out there once all of this stuff calms down. But in the meantime, I get to share some of the astronomy I used to work on with everyone, which I'm really excited about. And so today I'll be talking about exploding stars, dark energy, and the runaway universe. This was my area of expertise for many years when I was working in astrophysics. And so here we have a picture of a galaxy. We think this is what our Milky Way galaxy kind of looks like. It's got this big core of stars in the middle, sort of that little fuzzy bright blob in the center of maybe 100,000 or so stars, 100 billion stars. And then there's a supermassive black hole in the center of this galaxy, much smaller than a single pixel in the image. And then around that, you've got the sort of spiral arms. It's kind of tilted on its side, but you can see sort of dark arms where there's dust and then lighter arms where there's stars. But the main thing I want to draw your attention to is this really bright spot, this single star in the sort of bottom left part of this image. And this is an individual star that has gone supernova, that has exploded at the end of its lifetime in this galaxy. So we have one star that has now become about as bright as 100 billion stars in the core of this galaxy. So this is a hugely powerful explosion. This can eject up to, the same amount of material that the entire sun weighs. It can build up enough iron in this explosion to make over 5,000 Earths. The material that gets blasted out is moving at something like 10% the speed of light when it's moving its fastest. And so these are incredibly powerful explosions. The amount of energy output by one of these explosions in about a month or two is similar to the amount of energy that the sun will output in its entire 10 billion year lifetime. So incredibly powerful in just this huge explosion going off from one single star at the end of its lifetime. Not all stars will go supernova at the end of their life. They either have to be very massive, like 8 times the mass of the sun or bigger, or they have to be very close to a companion star and sort of interact in some way with that star. And so to get sort of at the beginning of the story of our modern understanding of supernova, we have to talk about this curmudgeonly old fellow, Fritz Zwicky, very famous for doing a lot of amazing groundbreaking astronomy, including doing one of the first consistent searches for new exploding stars, looking for these supernova and then trying to actually understand them. He coined the term supernova in 1926. That word comes from the Latin word nova for new. So ancients used the word nova to describe a new star that popped up in the night sky. And then Fritz and others figured out that there's sort of smaller classical nova, and then there's these supernova, these really big new stars that explode. And so that's what I'm going to talk about today. Quick aside about Fritz, he, as you can see, is kind of a cranky old guy. He would call people spherical bastards because they were bastards every angle that you looked at them from. So he's definitely an interesting character in the history of astronomy. Getting back to supernova, though, humans have been observing supernovae for basically the entire time in recorded history. Most of that time, we just didn't know what the hell we were looking at. They were just a bright new star in the sky. And so one of the most famous supernova in history is a star that exploded about 1,000 years ago. And so when a star explodes, it blasts off all this material, this gas and dust. It's expanding out very quickly. There's a lot of it. And then that gas and dust can slam into other kind of material sitting between stars, minding its own business. So when you have that big collision, it heats up, it starts glowing, and then you get what we call a supernova remnant. And so that's what we see in this picture here. This is the Crab supernova remnant in the constellation of Taurus. And so this is from a supernova that went off in the year 1054. And 1,000 years later or so, 1,000 years and 1,050 years later, the Hubble Space Telescope will take a picture of it, and this is what we see today. So this is the sort of leftover exploded remnants that's crashed into the stuff between stars. And so this supernova went off in the year 1054, and we have plenty of records of the observations. Basically every civilization in the Northern Hemisphere, from the Far East to the Middle East to the Americas, witnessed this exploding star, this new star that popped up in the night sky, and recorded it. In 1054, there were some issues in Europe. We don't have too many records from then, but basically everywhere else in the Northern Hemisphere saw this and wrote about it. This new star was visible during the day for 23 days. And was visible at night for about 653 days, so nearly 2 years. This was visible at night well before the invention of the telescope. And we think this potentially was one of the ancient observations of the Crab supernova from 1054. We have the sort of star-looking thing towards the bottom left. That might be the new supernova. It's not totally obvious. We have the crescent moon where it was in the sky when they first saw this new bright star and sort of its relation in the sky to where the new star was. And then the artist's hand for scale. This comes from the Anasazi people in Chaco Canyon, New Mexico in the US. And so this is a rock drawing from around that time, around 1054. And so maybe this was somebody's PhD thesis 1,000 years ago, something like that. And so here's a series of images of a supernova, of a star exploding over time, sort of a time lapse. This is from an amateur astronomer, so someone who lives in a dark area with a pretty big backyard telescope. Not quite as pretty as that first picture I showed, which is from the Hubble Space Telescope. But still, we have that bright core of stars, the nucleus of the galaxy in the middle there. It's sort of tilted on its side, but there are sort of spiral arms above and below the core. And then we see the single star, this supernova going off in this galaxy. And the whole series of images is about 3 months. And that's pretty typical for a supernova. It takes about 2 or so weeks to go from exploding to the maximum brightness, the brightest it gets, and then it kind of fades away over the span of a few months or so. And that's pretty typical. Some supernova, if they're really powerful or weird or very close, we can observe for years or even decades. But typically the ones we look at in other galaxies, they're going to be sort of alive for about a few months and then too faint for us to see anymore. All right, so why should we care about supernovae? Well, these are hugely powerful physical explosions that happen naturally in nature. And so if we want to understand how large explosions happen, how you can produce these elements, how nuclear fusion ends the life of a star inside of a star, we want to study supernovae. And then we also have the explosion. The material that's blasted out can make these beautiful supernova remnants, but they also sort of jostle that gas. They kind of shake it up. And when you start shaking up gas, it might kind of clump up because of gravity and start collapsing on itself. And that's how you get a new star to form. So you can literally have the death of one star lead to the birth of new stars. It's very circle of life. I'm a big Disney fan, so I like that. This is also the only place in supernovae and other explosions involving stars where you get elements like oxygen and silicon and calcium and iron. And so those are built up inside of stars and then released through these kinds of stellar explosions. And so the oxygen we breathe, the calcium in our bones, the iron in our blood, that was all cooked up inside of a star. It's the only place that naturally happens, and then exploded outward in a supernova or other kind of stellar explosion, and then eventually gets incorporated into the sun and the earth and us. And so the American astronomer Carl Sagan used to say, we're all made of star stuff, and it's very hippie and nice to think about, but it's literally scientifically true. We are all made of star stuff. We can also use certain kinds of supernova to track the expansion of the universe, and that'll sort of be the last little bit of my presentation today. I'll get into that. So how do we find supernovae? Well, we use mostly robotic telescopes. There are some people, mostly amateur astronomers, that are looking by eye. But for the most part, we use robotic telescopes. So they're robot telescopes around the world. This is one out in the western part of Texas in the US that I used to use. And so this telescope doesn't have anybody running it or looking through it or anything like that. It has weather sensors. It knows when it's clear, it knows when it's nighttime, and it knows what galaxies are in the sky each night. And so it'll just start taking pictures of those galaxies and comparing those new pictures to old pictures and trying to see, is there a bright new spot? And is that new spot maybe a new supernova? And so we think in the universe about every second, there's probably 10 supernovae going off. So during my pause, 10 stars exploded somewhere in the universe. And most of those, the vast majority, are way too faint, way too far away. We're never going to find them. But on Earth, with a lot of these robotic telescopes nowadays, we're finding dozens, pushing even hundreds of supernovae per night with some of the biggest supernova searches that are going on right now. And so, like I said, we take digital images, just like your digital camera or DSLR, of the night sky of galaxies, and then we compare them to old ones and look for a new bright star. So the picture on the left doesn't have a supernova. The picture on the right does have a supernova. And so you have to go, point by point and see, okay, what is there a new point, and does it look like a supernova? Does it look like a bright, real new star? And so this one, there's a lot of points to compare, but the supernova is actually pretty bright. So this is a relatively easy one. And so I will point it out for everyone. There it is. And so originally we had undergraduate university students looking at these images by eye every night. And, modern telescopes are taking hundreds, if not thousands of these images. But, there's only so many university students floating around. And so we had to get a little bit smarter. And so now we have pretty advanced image difference algorithms that can kind of do this automatically and very efficiently and quickly, and then sort of automatically alert astronomers that, hey, there's probably a new supernova here. And in some cases, even trigger automatic follow-up from other telescopes to get more data and see, yes, is this real? Is it not? Is it interesting? Should we get even more data, etc.? So, okay, let's take a look at some actual data. This is a science talk, so I'm going to show some graphs. This is real data from my old research group at UC Berkeley. And this is what we call a supernova light curve. So this is a graph of the brightness of the supernova plotted against the days since discovery. So just time on the horizontal axis. The different colors are different filters that we can put in the telescope to get other information about what's going on here. And this basically shows sort of what we saw in that time-lapse series I showed earlier. It takes about 2 weeks to go from explosion or discovery to its maximum brightness. And then it sort of fades away over the span of a few months, 2 to 3 months or so. We can learn a lot from these. We can learn how bright the supernova is, obviously. We can get an idea of how much energy or maybe the temperature of the supernova. We can get an estimate of the distance of the supernova often from this kind of data. But this wasn't really my specialty when I worked on exploding stars. My specialty was listening to classic rock late at night and doing what this Pink Floyd album cover is showing us, breaking up the light from a supernova through a prism into its rainbow, into its component colors, which we call a spectrum. And so I can graph the spectrum or the brightness versus wavelength and get what is called a spectrum. And so the wavelength is just the color of the supernova or of the light coming in. That's the fancy physics word for color. And on each of these graphs, I've put the rainbow, the wavelengths of colors that we can see with the human eye, all the way from purpley blue on the left to reddish on the right. you can see that these observations of supernova, these spectra, cover a little light that's a little bit bluer than blue or more violet than violet, so that's the ultraviolet. And then on the right side, we go a little bit redder than red or infrared. So this covers sort of the ultraviolet, optical, and infrared. And these are actual data. These spectra appeared in my PhD thesis. You can look it up online. They're real. And what's cool is we can learn a lot more about the supernova from these kinds of observations. We can learn about the elements that are in the exploding star. We can learn about how fast the material is moving as it explodes outward. And we can get a much better idea of the sort of makeup of what's going on in this explosion and how it evolves with time as the explosion continues and eventually cools off. Scientists have known for 150 something years that in a spectrum like this, every bump and wiggle, and yes, those are technical terms, can be associated with an element on the periodic table. And so I can look at the top left spectrum and see, that big thing in the middle is H alpha, hydrogen alpha. And then the sort of the top spectrum toward the right, there's some calcium. And then the bottom spectrum has sulfur and silicon, along with calcium and oxygen, iron, magnesium, etc. Some of those elements I was mentioning earlier that are inside of us. And so time for some vacation photos. Here are a couple of telescopes where I got spectra. These are the twin Keck 10-meter telescopes. And because this is a not American audience, I don't have to convert meters to some other silly unit. So these are 10-meter telescopes. That means that the biggest mirror in these telescopes are 10 meters across. You can't really see them. They're the sort of inside the dome at the bottom. But if you look sort of to the bottom right of the left dome, you might see a little car sitting in front of the building. That's a full-size SUV, just to give you kind of an idea of the scale of these things. These are on the dormant volcano Mauna Kea on the big island of Hawaii. And so these have done amazing astronomy in all different kinds of subjects, but I did actually get some data from there for supernovae. And here's me a number of years ago posing in front of the Keck Observatory. This was taken in August in Hawaii. So, that morning I was on the beach in board shorts and flip-flops. You go up 14,000 feet above sea level and you are, you have to wear your ski jacket and your jeans and your hiking boots because it gets chilly up there. Here's another famous telescope that's done a ton of astronomy and has also done a lot of supernova work as well. This is, of course, the Hubble Space Telescope, which is about the size of a school bus, just to remind people. There's no cars near it or me to give you a sense of scale, unfortunately. And so what astronomers were doing in sort of the late 90s with Hubble and with some of the biggest telescopes on Earth down in Chile and in Hawaii was just like what I talked about earlier with those robotic telescopes. They would look at galaxies, they would come back a few days later, a few weeks later, look at those same galaxies and look for bright new stars or points of light that could be bright new supernovae. And when we do this with some of the biggest telescopes on Earth and in space, we can look even further away. And so sort of in April and May of 1997, we were finding supernovae that were billions of light years away, as opposed to a mere 100 million light years away, like we normally do from Earth. And so by measuring the brightness of these furthest away supernovae, we could actually track the expansion of the universe. So I'll take a quick little detour before I get into the last little punchline of my presentation. So I'll talk a little bit about the Hubble expansion of the universe. So here's a picture of Edwin Hubble, namesake of the Hubble Space Telescope. Back in the good old days where you could smoke your pipe right at the telescope. They frown on that nowadays. They don't let you do that. Okay. In addition, in 2018, the International Astronomical Union realized that they should actually call this the Hubble-Lemaitre expansion to recognize the contributions of Georges Lemaitre, who was actually a Belgian Catholic priest and astronomer who did similar research to Hubble. He published his findings 2 years before Hubble, but he didn't get any credit because he published in French, and we all know French isn't a real science language. I think I'm mostly on with English and Spanish speakers, so I can say that. Okay, anyway, so now we call it the Hubble-Lemaitre expansion, and so what is this? Well, they and others realized in the 1920s that all galaxies are moving away from each other. All galaxies have mass, they have stars and dust and stuff. And so Newton told us a few hundred years ago that because they have mass, they should pull on each other through the force of gravity. So you have the stuff expanding away from each other, pulling on each other through gravity. All that pulling should slow down the expansion. That's the idea. So we can measure the distances to these faraway supernovae. We can measure how bright they appear, how far they're away from us, how fast they are expanding away from us. And it basically broke all of cosmology. To basically make everything work out correctly, they had to invent something new, and what we now call dark energy. So the idea that the expansion is accelerating with time, that something is pushing against gravity, that we've now called dark energy. And so these three fellows in 2011 won the Nobel Prize in Physics for discovering the accelerating expansion of the universe through observations of distant supernovae. So this is totally unexpected. This is really bizarre, something working against gravity on the biggest scales of the universe to make galaxies move away from each other faster and faster. And so at first, I said these results were figured out sort of in 97 and 98. And, at first other astronomers thought that the supernova folks were smoking something. They were crazy. There was, something totally wrong. But since then, it's been confirmed with more supernova observations and other astronomy observations that have nothing to do with supernova. So the accelerating expansion is real. We've termed it dark energy, and we don't really know what the hell it is. So Saul, Brian, and Adam split the Nobel Prize for this. There's been lots of fun celebrations over the years for the Nobel Prize and for other awards that this research has garnered. I got in on the action one of my trips to Australia, posing with Brian Schmidt, who actually owns a winery in Australia. So he produces wine with supernova themes occasionally. So I get to try that fresh off of the winery down there outside of Canberra. Okay, so we don't know too much about dark energy, even though it was discovered, over 20 years ago now. We do know it makes up a hell of a lot of the universe. So at least 2/3 of the universe is made up of dark energy, possibly more. There's a whole presentation that could be given on, how this pie chart actually breaks down and who's right and who's wrong. Most of the rest of the universe is dark matter. Whenever an astronomer uses the word dark in a term, it means we just really don't know what the hell we're talking about. We don't really know what it is. So dark energy, pushing galaxies away from each other, we don't really know what it is. Dark matter, something that's pulling galaxies, stars within galaxies together to keep them in their nice spiral shapes, and we don't really know what that is either. Intergalactic gas, that's like hot hydrogen kind of between galaxies, that makes up about 4% of the universe. And then the last 1%, stars, planets, and other stuff, a tiny fraction of that being planets, people, puppies, kitties, beer, etc. So this is the point where everybody feels very small and insignificant and that we don't really understand the universe. But I will point out, as far as we know, of this entire pie chart, we, humans, are the only part of it that can actually sit here and drink beer and coffee and tea and cider and think about this and try to understand the rest of the pie chart. So maybe that makes you feel a little bit better. And with that, I will finish up and pass it back to Rachel. Thanks.
Wow, thanks very much, Jeff. That has made us feel both small and significant at the same time. So thank you for that.
Perfect.
Now, those who are watching on YouTube, if you have any questions you would like us to put to Jeff, do pop them in the YouTube chat and we will ask them live. I'll start with some of the ones that we've already had in. Earlier on in your talk, you showed a picture of the Keck Observatory and said that the mirror is 10 meters across. Does that mean a single piece of glass that's 10 meters in diameter?
Great question. So, the short answer is no. For the Keck telescope, for some of the biggest telescopes in the world, they actually make smaller segments. The Keck segments, I believe, somebody on the call could correct me, I believe they're about 1 meter to 1.5 meters across. And they're hexagons, and they sort of kind of fit together like a honeycomb or soccer ball kind of thing. And you kind of combine all of them together to get a total size of 10 meters across, but they're made up of these much smaller individual pieces that they can swap out and clean and tweak and stuff like that. And so that's much easier to build a whole bunch of 1 meter segments rather than one 10-meter segment.
Yeah, because they have to be really, really precise, right? You can't have any little bumps, and that's pretty difficult to do. A 10-meter sheet of glass is pretty heavy.
Yeah.
So onto the supernovae. How can you be absolutely sure that all of these supernovae are the same brightness?
Yeah, so I sort of hinted at using supernovae for distance measurements and kind of assuming that they're the right brightness. So first off, supernovae are not the same brightness. There are many different flavors of exploding stars with a wide range of brightness. Ballpark off the top of my head, it's probably, the maximum brightness range for all kinds of supernova is probably a factor of 10,000-ish, maybe more in energy and brilliance. What we can do is we can look at subsets of supernova that look very similar to each other. So certain kinds of supernova look very similar. And even those that look very similar, we actually have to apply a correction. And so I said that on average, supernova take, sort of a couple weeks to get to their maximum brightness. we actually have found that even with a very consistent set, a certain kind of supernova, the ones that get bright faster actually are fainter, and the ones that get bright slower are actually a little bit brighter. And so if you measure how fast it gets bright and how fast it fades away, you can actually kind of correct for that maximum brightness, or that sort of power output, the 60-watt light bulb kind of thing. Then you can say, okay, then we think we have a corrected value, a standardizable candle is what we call it, instead of a standard candle. And then once you have that, then you can say, okay, I know this is putting out this much energy, this much brightness. Once I make the correction, how faint does it appear? And the fainter it is, the further away it is.
So for supernova observations to have led to a conclusion as massive as dark energy, like, you have to be really, really certain of your observations before you're willing to like break physics.
Yep.
How embarrassing would it be if it just turned out that the supernovae the furthest away are just intrinsically fainter?
Yeah, so that's certainly a concern. One of a laundry list of concerns that, there were two teams that sort of did this research in 1997 and 98. A laundry list, one of many concerns that each of those teams had. They worked very independently. So the fact that two groups got the same result using different data, different analysis techniques, different, methodologies, but sort of the same basic ideas was good, but it's not perfect. Each team had these lists of, what ifs, what if this was wrong? What if this assumption is wrong? What if, further away supernovae are intrinsically different? And they tried to check those off as much as possible in those initial papers. And that's, part of the reason why it took 13 years to get a Nobel Prize. Other teams had to get more data and check that, other ways of measuring the expansion, accelerating expansion of the universe, using other stuff in the universe that's not supernova. So that all seems to be real. Now, as we start getting into the details of how much dark energy, how fast is the acceleration, et cetera, then you start getting concerned about these like smaller effects, like maybe the furthest supernova are weird for some reason. They have different chemical composition. We know that. They might have slightly different, brightness and things like that. And so that's where you start to play with the game of sort of big data and statistics. I'm a data scientist nowadays. And so that's sort of the techniques that you start using, is if you have enough far away supernova, you can randomly sample them and see how similar are they. There are statistical tests to say, well, there's some range of brightness for the far away and the nearby ones, but do we expect it to overlap, or are they really distinct? And so people are starting to play that game as we get more and more observations of these very far away, very faint supernovae. And there seems to be maybe a hint of some things being different with the farther away ones, but way, way more subtle than any measurement of dark energy that we have. And still within the uncertainty of maybe they are the same, maybe not, but certainly still active investigation, active research.
And that's what makes science interesting. So one more question before we let you go. How does an astronomer see in the dark?
How does an astronomer see in the dark? I feel like this is a bad dad joke or something.
With a standard candle.
Great. Not a standardizable candle. That was the whole point of this talk.
That's a less catchy punchline. You're rubbish at this. Thank you so much for being with us this evening, Jeff. It's great to see you again, and it's great to be able to have you in Edinburgh virtually. So
I'd love to see y'all's castle at some point. Cheers.
All right, now, so at Astronomy Off Tap, we like to have some fun with our science. So as well as learning lots about the universe, we like to have some fun games. And we have a new game this month. So I'd like to welcome John, who is going to present the game to us.
Thank you, Rachel. And thank you, Jeff, for that brilliant talk. That was really, really interesting. So as Rachel said, this is the point of the evening where we sort of dumb it down a little bit. We go a little bit lowbrow with the games. So I'm just going to share my screen very quickly so everybody can see. Bear with me. So this is a bit of a brain teaser this month. So I've given you 6 different scrambled space words. So essentially each of those 6 words has been scrambled into an anagram. Some are 2 words, some are 1. I can say 2 of them are 2 words, the rest of them are 1 word. And your job is to unscramble these anagrams to make any kind of space word. So they're all specific astronomical or space terms. You have to unscramble those. Once you've managed to unscramble all 6 of these, then you'll be able to rearrange the first letter of each word to spell out one astronomical term. So that's your challenge. So it's a little bit tricky this time. You've got a bit of thinking going on there. What we'll do is we'll share this on Twitter as well and on our social media so people can kind of see it and have a bit more time with it. And we will share this a little bit later on as well. So what we'll do is I'll leave it up for a little while now so everybody can kind of have a look and have a think about it. But basically, yeah, your job is to sort of take these words, unscramble them, use your sort of fantastic array of brains that you've got out there watching the stream, and see how you get on. So I'll leave this up for a little while, but we will share it on a little bit later on. I'll give you another sort of 5 to 10 seconds just to have a look at those, note them down, start unscrambling. I just would say, if anybody does get it, if anybody out there is like a speed pen, please do post it up on YouTube on the comments section, or you can tag us on Twitter, or you can post it on our Facebook page. If you do find out what the mystery word is, please do post it up. There isn't a particular prize for this one, except our undying respect for being incredibly good with words. Although if anybody does put it up and they're really good and we know them, or you put up some details, we might be able to send you a European Space Agency poster, because we still have about 3,500 of those sitting somewhere in Edinburgh. So that's always a bonus. All right, Rachel, I'll hand back to you, but we will share this later on, so don't worry if you haven't got everything through.
Now, I hope someone else gets those, because I am appallingly bad at acronyms. I had to set an acronym quiz with one of my other hats on recently, and going through the answers, I had to have them up in front of me, even though I made them. Not my specialty at all. So while you're all working on those, we're going to move on to our second talk of the evening, which is also about things going bang in space. I'd like to welcome Emily Petroff, who is an astrophysicist working at the University of Amsterdam as an NWO Venny Fellow. Her work focuses on finding and understanding mysterious astrophysical transients called fast radio bursts, and she is one of the founding members of this new and exciting field of research. So if you're thinking you haven't heard of fast radio bursts, that's why it is very new. In her talk, she'll introduce these mysterious but seemingly common bright radio bursts and talk about the bumps along the road that led us to our understanding of these distant sources. One fun fact about Emily, she has a corgi named Delta and spends most of her free time on walks or throwing a tennis ball. I feel like this is a common theme in astronomy, nerdy pet names. We'll have another one a bit later on as well. So welcome, Emily.
Hi, Rachel. All right.
Welcome to Astronomy Off Tap Edinburgh, and take it away.
All right, thank you so much. Let me get my screen shared and start my talk. All right, so thank you so much for having me here, everybody. This is my second Astronomy on Tap, well, Astronomy Off Tap, I will say, in the past, during the COVID times. And I actually, you know, I hope to go to a real live Astronomy on Tap one of these days, but for now I'm pretty excited to give you this talk, even though it's remote. So I'm going to tell you a little bit about my work on these things called fast radio bursts. But fast radio bursts is despite being a very new topic, is a very big one. So there's a lot to talk about these days. And so instead of trying to encapsulate an entire field of research in 15 minutes and really not do it the justice that it deserves, because I could talk about these things for hours and hours, I want to talk about a sort of anecdote that happened along the way of trying to understand fast radio bursts. So I'm going to call this talk instead something like that time I didn't find fast radio bursts. Yeah, so I have to start the talk by telling you about fast radio bursts. Hopefully you've heard this term before, but if not, we'll start from the very basics. So you might be asking yourself, what are fast radio bursts? Well, that's a very excellent question. One that I wish I knew the full answer to myself. In fact, from Jeff's talk, he said if we don't really understand something in the universe, we should call it dark. So I guess we could call these dark fast radio bursts. We truly don't understand a lot about them. This is what a fast radio burst looks like in our data. We collect the data with radio telescopes around the world, and you can probably guess where the fast radio burst is in this data set. This is just our data coming in off the telescope as a function of time, and that very, very bright spike that you see in the data is the FRB. This spike lasts somewhere between a few microseconds to about 10 milliseconds. So that's anywhere between 100 and 1,000 times faster than the blink of a human eye. So these are incredibly short, bright flashes, and you can see how bright they are relative to the sort of noise baseline of our telescope. And these are coming from sources billions of light years away. So like the supernovae that Jeff talked about, these things are coming from distant galaxies, from some sort of very extreme event that's happening there. They're hugely energetic. So within this single millisecond spike in our data, there's more energy than in that single spike than the sun gives off in an entire day. So these things are really packing a lot of energy into a very short amount of time. In fact, they're one of the shortest astrophysical transients that we know about that's out there right now. And we think that there are about 5,000 fast radio bursts detectable over the whole sky every day. So where Jeff mentioned that there's many, many supernovae happening outside in the universe, the rate of fast radio bursts is lower than the rate of supernovae, which is good, because if they're coming from something like stellar explosions, they'd have to be less, there'd have to be fewer of them than supernovae. But we think that we could, if we had a perfect telescope that was just constantly looking at the whole sky all the time, we could detect up to about 5,000 of these events every day. So this is, these have to be something really common. They have to be something really energetic, and they have to be something really short. So you're thinking, you may be thinking, okay, like what fits that budget? What are these things? And that's a really great question. If you can answer that question, we would be happy to hear your answer, and you would be in good company with the many theorists trying to guess where fast radio bursts come from. Right now, we have something like 500 plus fast radio bursts that have been discovered by telescopes around the world. Unfortunately, only about 100 of those have been published so far. We have a bit of a backlog that we're working through, and you know, we're finally at the point where we're finding them faster than we can publish them. But the ones that are published are on this catalog online that I run called FRB Cat. So if you're curious just to see what they look like or how many there are, you can head to that website and just kind of see what's available or what's published and public right now. But if, you know, there are so many theories for what causes FRBs. For a while, we lived in this regime where there were more theories than there were fast radio bursts. And now we are somewhere, now we have many more fast radio bursts than theories, but there's still something like 70 or 80 theories out there for what could be causing fast radio bursts. And in fact, there is not just an FRB catalog, there's an FRB theory catalog as well. So there's lots of active theorists out there busy thinking about how you could get an FRB. And it's really anyone's game right now. This is why it's kind of an exciting field for theorists, is because there's just so much potential to put your idea out there. So there's lots of ideas floating around, from things like collapsing neutron stars or colliding neutron stars, some more exotic things like white holes or cosmic strings, or some more local things. Instead of saying they're fully, they're like at very large distances in the universe, that they're actually coming from things like young neutron stars kind of nearby in the universe, or from giant pulses from neutron stars. A lot of the theories right now are kind of focusing in on neutron stars. So what's left over in like the Crab Nebula that Jeff showed. Sometimes there's a neutron star that's left over after a supernova, and these can be extremely magnetic, energetic, compact objects. And we've never seen anything quite fast radio burst like from any of the neutron stars in our own galaxy, but we're starting to get close to seeing things that might hint at a link between neutron stars and FRBs. So that's quite exciting. But I don't want to spend all my time talking about FRBs, even though I could do so happily for hours and hours. I want to tell you a story about the time I didn't find fast radio bursts, because it's one of my favorite stories from my entire time as an astronomer, and possibly the most fun that I've had on any paper that I worked on. So the story starts at the same time as the story of fast radio bursts, which is in 2007 at the Parkes telescope. So Parkes is where I did all of my PhD work, and it is also the telescope that was mainly responsible for the first boom of fast radio burst discoveries, because in 2007, the very first fast radio burst was discovered in some archival data from 2001. And this is a plot from that paper. It was published by my colleague Doug Lorimer, and so we call it the Lorimer burst. So this was an extremely bright pulse that was found in the radio data. It lasted about 5 milliseconds, so very typical for an FRB. And what's interesting here is not just the duration of the pulse, but it's also how the pulse arrived at the telescope. So for astrophysical signals, they have to travel through, the ionized interstellar medium or the ionized intergalactic medium. It's this plasma soup of electrons and positrons. And as a radio signal travels through that plasma soup, you see something that looks like this in the data. You see, if you observe over a radio bandwidth, so a range of radio wavelengths, you actually see that the shorter wavelengths at the top arrive earlier and the longer wavelengths at the bottom of the band arrive later. And the slope of this curve tells you how many electrons the pulse traveled through, or roughly how far away it came from. And with the Lorimer burst, the slope of this curve was so much larger than what we would expect from the electrons in our own Milky Way galaxy, which led us to believe that it was coming from not even our galaxy or a nearby galaxy, but a galaxy potentially billions of light years away. And it was the first time that we'd seen such a bright pulse that had a potentially extragalactic origin. So this was incredibly exciting to us. And this is Dunk here, and he said it was unlike anything we'd ever seen before. So of course we were extremely excited about this. And so when you find something that's unlike anything you've ever seen before, you try to find more of them as hard as possible. So we tried to go back and look through all of our old data and take new data to see if we could find more fast radio bursts or more Lorimer bursts. And so it would be really nice if our data analysis looked something like this, where you just take your giant chunk of data, you press your data analysis button, and then some answers pop out. But I lived the hard life of a grad student for many years, so I'm very aware that it often looks like this instead, where you sit at your desktop and hopelessly stare at millions of plots trying to find something that looks like the Lorimer burst. And that's exactly what we were doing. So one of the PhD students working at Swinburne, where I did my PhD, her name was Sarah Burks-Valor. She was looking through lots of data to find more Lorimer bursts. And in 2010, she found this pulse. So this looks kind of promising. It's a few milliseconds long, and you see this sort of sweep across the band like you saw for the Lorimer burst, but it's patchy. It doesn't look quite right. We got really excited though, because, it's the first time we'd seen something similar in the data, but we very quickly started to lose a little bit of hope, because what was kind of telltale about this burst is that we saw it in all of the pixels of the telescope at once. So a radio telescope has much bigger pixels than something like a digital camera or something like that. But just like a normal digital camera, if you see something on the sky, or you see something that has a finite location, you should expect to see it in a few pixels, maybe 1 pixel or a few, depending on how bright it is. But if it's something that's just saturating the field and is really nearby, you would expect to see it in all of the pixels at once. And so at the Parkes telescope, we have 13 pixels. It's very advanced. And we saw this signal in all 13 pixels at once. And this never happens for an astrophysical signal, even if it's very bright. This is a telltale sign that it's some sort of interference coming from nearby the telescope. And so Sarah called these events the peritons. In some mythical literature, I suppose, peritons are these winged deers that cast the shadow of a man. So they're basically something that is not what it appears to be. And in this case, we can just go ahead and call it a red herring, because that's exactly what they were. So she published the peritons in 2010. There hadn't been another Lorimer type burst published since 2007. It was really interesting to compare the two, because on the left you have the Lorimer burst, on the right you have the peritons. The Lorimer burst really is very broadband. It only happened in 3 pixels in the telescope, so you can see the 13 pixels on the sky here, and these are the 3 where it was found, whereas the periton was in all 13 pixels. So this kind of, I would say, it muddied the waters of what we consider to be astrophysical, what could be detected by the telescope. If you can get something local that mimics the Lorimer burst, could the Lorimer burst just be totally unreal? And so we started to get pretty disappointed. I would say a lot of people lost enthusiasm for the Livermore bursts and fast radio bursts around this time. And we were all very concerned about whether what we were seeing was in fact real. And so, we kept looking through the data. We tried to keep looking for more Livermore type bursts. And actually in 2013, 2014, we started finding more of them, which was great news. We started finding things that really looked like the Livermore bursts. They really appeared to be coming from really far away. But at the same time, we were also finding more peritons in the data. And importantly, both the fast radio bursts and the peritons had only been found at Parkes, at one telescope. So this was starting to get very embarrassing for us because perhaps you just have one sort of misfiring electronics at the telescope that's giving you a whole range of behaviors. And so you're seeing some of them as fast radio bursts and some of them as peritons. But we were kind of saved in 2014 when the very first fast radio burst was found at a non-Parkes telescope. So this was found at the Arecibo Observatory in Puerto Rico, which is as far from Parkes in Australia as you could possibly be. And this really looked like a fast radio burst, just like the other Parkes ones. So we were able to breathe a little sigh of relief and say, okay, so we see these fast radio bursts at two observatories. That's very good. If they're astrophysical, you should find them wherever. But we only see the peritons at Parkes. So the peritons are likely just some local phenomenon, and the fast radio bursts are well and truly real astrophysical objects. We can move on. So we continued with this line of research, and the field of fast radio bursts really started picking up the pace. So this was during the time when I was doing my PhD, and it was incredibly exciting to be working at this time. We started finding more fast radio bursts with more telescopes like Arecibo in 2014 and Green Bank in 2015. I found the first fast radio burst in real time at the Parkes telescope, and we followed it up with other telescopes around the world. We started finding many, many more FRBs kind of in bulk in the Parkes data. So we got really good at finding them. So we were really convinced that this is a real field. They're out there. They're pretty common. We don't know exactly what's causing them, but they're worth studying. And this was great. And so every time I would go to my PhD supervisor with a new FRB result, this is my supervisor, Matthew Bales, who would say, yeah. But what about the peritons? This question of the peritons really bothered him, really kind of kept him up at night. And I kind of understand that now that I've been in this field for longer, but he really he had a hard time fully investing in fast radio bursts until we'd solved the periton mystery. So I just kind of figured, okay, I'll figure it out. So I started looking at peritons. I started looking at archival data, but I also started, since we were starting to find fast radio bursts in real time at the telescope, we had really good algorithms for that. I started tuning our algorithms to also try to find the peritons in real time. This basically just amounted to summing all 13 pixels together and seeing if you see a bright pulse that looks like this. And lo and behold, we're able to find peritons basically right after they're discovered, right after the data is taken at the telescope. And so the advantage here is that after we found a periton, I could go back to the Parkes staff and say, I found something really weird in the data. What was happening at the telescope yesterday? And the Parkes staff came back to me and said, well, we're not sure what was happening yesterday, but you can check the interference monitor. And I said, okay, that's great. What interference monitor? So it turns out that at the end of 2014, the Parkes staff had installed a monitor at the site to monitor the radio frequency environment at the telescope, because radio observations are plagued by interference, be it from electronics, from satellites, from people, from televisions. Everything causes our data to get really messy. And so radio sites are supposed to be quiet. So they installed this monitor so that they could see what was happening on site and how different things affected the radio background at the telescope. And what we found was really interesting. So this monitor has a very coarse resolution, and it really just sweeps the entire environment, but it looks over a much wider frequency or wavelength range than we normally observe with the telescope itself. So you can see on the x-axis here on the bottom, we have the actual wave frequencies or wavelengths that this monitor looked over, something from around like 0.4 gigahertz up to like 3 gigahertz. And that shaded bar between around 1.1 to 1.5 gigahertz is where we normally observe with Parkes for FRB observations. But what we found is that when we found a periton at the telescope, at the exact time of the periton, there was this very bright spike that's highlighted by these arrows happening at 2.5 gigahertz. So this is well outside of the band where we're observing the peritons. So we never would have identified this from the data that we had just from the telescope itself. But this is an extremely important clue because if you're at all familiar with radio electronics or electronics of any kind, you know that 2.5 gigahertz is a very common frequency band for things like Wi-Fi, Bluetooth, cell phones, computers, laptops. But all of those things don't exist at parks, or if they do, they're meant to be very properly shielded. But the one thing that does exist at parks that you know, we were trying to look at turned out to not be any of those. So I also tried to start gathering archival data of peritons. I looked through lots of old observations to get a big sample of them. So in the end, I had something like 50 or 60 peritons that we'd found with parks. And if you looked at where the telescope was pointing when we saw these things, what we saw is that they only came from two directions. And this was a huge clue. So as you can see, the two directions were both buildings on site. The one on the left is the visitor center, and the one on the right is the staff shed where they have lunch and where they test electronic equipment. And so these places are kind of no-brainers for where, if you're getting electronic interference on site, this is where it should be coming from. So we're on the right track. The other little clue that we had was, since I had this large sample of them, I could look at their distribution in terms of time of day. So this is the distribution of the fast radio bursts that we found up to 2015. This is good. Fast radio bursts should not care what time of day it is. They should happen regardless of whether you are well rested or not. But if you look at the distribution of the peritons, they look quite different. They in fact only happen during business hours. And if you actually correct for daylight savings time so that you're just dealing with purely with local time, this peak around noon to 1 gets very, very tight. And you're seeing that the majority of the peritons happen around lunchtime. So this may be no surprise to you, but it turns out that you can produce a periton with a microwave oven. So to produce your very own periton, all you need to do is to be impatient for the microwave to finish and to open the door of the microwave before the cycle has finished and you've heard it beep. It turns out that while it's still running, there's a magnetron in there. While it's still running, if you open the door, you break the Faraday cage of the microwave, and a tiny little pop of emission comes out of the microwave at around 1 to 1.5 gigahertz. And the way that it curves around the cavity of the magnetron gives it this sort of swept signaling frequency. So you can make your very own peritons at home. You shouldn't worry that these are like somehow dangerous or harmful, because we needed a cooled receiver that's like almost at 0 Kelvin to be able to detect these signals. So we need a very powerful telescope to be able to detect these. But we tried several experiments with the microwaves. We kind of were on the right track. We knew it had to be the microwaves, but we couldn't quite get them to make the peritons. We were like microwaving different types of things in them and different cycles and stuff. And it turned out that the magic ingredient was just you pop the door before it's done. So this was great. It meant, and you know, if we actually went back and looked at the locations of the microwave ovens on the park site, which they are in shielded locations, but somehow human error does not account for this. The two microwaves are right here. So we are very relieved to say that the microwave ovens are absolutely 100% responsible for the peritons. So this is great. I could go back to my PhD supervisor and say, you know, he says, what about the peritons? I say, no worries, they're only microwaves. And we can get back to FRBs, which is, you know, where I prefer to live. The field of FRBs is absolutely booming, pun intended. We're finding so many of them with so many different telescopes around the world. This is a plot from a review article that I wrote last year, and it's already completely out of date. We're finding something of order like tens per month now. So we're learning so much about them. We still don't know where they come from, but we're working hard towards an answer. But we do know that FRBs are definitely 100% real, and we're very confident about that because we can put to bed the whole issue of the peritons. And so I like telling this story because I think there's a really nice lesson about the joys of finding something that you weren't looking for. And this was sort of like the biggest science lesson that I think I learned during my PhD, which is, this had all the elements of like a fun detective story in terms of like trying to hunt down the source of these mysterious signals. And we got to work with the park staff, which was super fun. We're way more confident that FRBs are real than if we had purely ignored the peritons and just said, yeah, we know that they're interference. So it is really worth doing this follow-up work to be 100% confident in your real science results. This is actually also my most downloaded and read paper of all time. I think it's been shared in like more journal clubs than any other paper out there, besides maybe the gravitational wave papers. It's the third most downloaded paper off of the physics archive, which is like one of my favorite statistics. And this is truly how real science happens. You have a problem or you have a question that you're trying to answer, and then you go out and collect your data, you analyze it, you test hypotheses, and then in the end, hopefully you get a satisfying answer to your question, but in some cases you get more questions. And then also I think just it's, it makes for a super great story because this was all over the press. I love all these, it's a little frustrating sometimes, but it is quite funny to see all these headlines about, how astronomers are baffled or stumped. They love it when we're baffled. And I think my favorite one was the cosmic microwave oven background. So, dabbling in a little bit of microwave cosmology there. So this was a super fun experiment that I got to do. And I think it just makes for a really great story. And I hope you enjoyed hearing about it. And I hope you're curious about FRBs as well, because there's a lot there too. So thank you so much.
And thank you so much, Emily, for that story. I remember reading about that at the time, and the way a lot of the news reports made it sound was like the entire field of FRBs turned out to be nonsense. So it's really good to know that's not true, that it was just one very specific thing. And as you say, it is better to have investigated that and found an answer than have just ignored them. So we have some questions from our viewers. The first one is, how can you tell what direction these FRBs are coming from?
Yeah, that's a good question. So the telescope is pointing in a direction on the sky. And because we have those 13 pixels, if you see it somewhere inside those 13 pixels, you can say roughly where it's come from. But we don't have very good, resolution on most of our radio telescopes. So you can say vaguely where on the sky it came from, but most of these fast radio bursts haven't been well pinpointed. It's only in the past year or two that we've actually been able to use telescopes like the Australian Square Kilometre Array Pathfinder, ASCAP, to pinpoint exactly in a galaxy where these FRBs are coming from. And there you can say for sure they're coming from galaxies billions of light years away. But for most of them, we just get a rough idea based on where the telescope is pointing.
So is it possible with current telescope technology to identify the progenitor of the FRB, or is that still some way away?
It's pretty hard because as soon as you get outside of the local group, you're limited by how powerful our telescopes are, really. So our closest fast radio burst that we have so far is something like a few million light years away. So it's still very, very far away and difficult for us to exactly pinpoint exactly like what star or what event caused it. You can definitely say where in a galaxy it came from, and you can say, oh, it actually came from this really super interesting active part of this galaxy, but we can't perfectly pinpoint the exact progenitor of the FRB yet. Hopefully we'll get more that are closer by, and then those will be like our dream laboratories for the rest of the FRB population.
And I really like this question. How does working from home affect searching for FRBs? Is it easier or harder?
That is a great question. It actually might be a little bit easier, I would say, because the nature of being a transient astronomer, so dealing with things that happen sort of unpredictably that require very fast response, especially so for optical astronomers, you already know it's just going to be at night. For radio astronomers, it could be literally any time in a 24-hour window. So working from home, I think, has given me like a bit more flexibility to work on these things. FRBs tend to like to go off during our observing run when all of us are like commuting or, in a meeting or something like that. So it is kind of, it's working from home has made it a little bit easier to respond quickly when we find something new. There's always someone available, which is good.
Yeah, that's interesting. So where do you see this field headed to in the near and long term?
Yeah, so I think in the near term, the big name of the game is not only finding more fast radio bursts, but also localizing them. So there's a telescope in Canada called CHIME, which is doing basically a lion's share of FRB discovery these days. It has a detection rate of something like 2 to 5 FRBs per day. So it's really, and other telescopes don't come anywhere close to that. It's just because it looks at such a large part of the sky at once. So CHIME is really good at finding FRBs, but not good at localizing them. And then there are other projects out there that are not so good at finding FRBs, but very good at pinpointing where they come from. So I think the near future is going to be sort of combining these two approaches to actually find host galaxies for a large sample of FRBs and see if we can see some sort of pattern or trend emerging. And then I think sort of the long-term future is if we can get a large sample of FRBs that we have host galaxies and redshifts for, that we can actually start to do some cosmology with them the way that the supernova community has done cosmology using supernovae as kind of cosmic rulers. FRBs can't quite be cosmic rulers, but they can be cosmic way scales, where we actually can use them to measure how much material is in the space between galaxies, which is really difficult to do any other way. So once we have a large sample of them, we can start to make those sort of precision cosmology measurements.
Now, how does it feel to announce such a huge discovery? Was it exciting or nerve-wracking or both?
For the peritons, I did not even think about it. I thought because we had spent so much time just trying to answer it, it felt very satisfying. So we're like, okay, great, we did it. It's fine. We literally just put it on the archive. I mean, so it's like a public repository for papers. We submitted it to a journal, but we didn't really think that it would kind of get the attention that it did. But I think because the paper was kind of short, accessible, the result, the end result was funny. It just kind of got totally picked up by everyone, and we weren't expecting any sort of media or anything. So I put it on the archive while I was on like a work trip, and was like, okay, well, it's out there. And then I was, in Germany visiting collaborators, and my Twitter started like blowing up with like all these journalists and stuff. It was totally unexpected, but I guess in the best way possible. People like really took to the result, and we hadn't even thought that it would be of public interest, really.
Yeah, I mean, I remember it because I didn't even look at the paper because I don't read radio astronomy things. I read about it on BBC News, so that was a pretty big thing. So how much data does that telescope collect, and how much do you have to sieve through to find your FRBs?
Yeah, radio telescopes take a lot of data. So the telescope that I currently work on in the Netherlands, it's a 12 telescope array. And in about 10 minutes, we take several gigabytes of data. So we're taking, the equivalent of something like an HD movie of data every couple of minutes. And in the course of an observing run, we basically collect more data than the entire internet of Western Europe collects in a day. So it's incredible throughput, and we use these giant supercomputers to crunch through the data to basically look for these little needles in the haystack. And because of computer technology has gotten so good with graphics processing units and things like that, we can actually do effectively real-time searches of the data and then be able to identify FRBs very quickly. So it's mostly automated now, and we just kind of, as the observers, have this very nice system where we just get a plot in our email or something. And so it says like, does this look like an FRB? And you can react. So that's quite nice. But in the early days, I think I was trying to add it up the other day. I think I literally looked at something like 10 million plots over the course of my PhD. So it's a lot of sifting for sure.
Wow, and that is why PhD students exist.
Yes.
Okay, one last question before we let you go. How many radio astronomers does it take to change a light bulb?
If it's at the Parkes telescope, well, it took us, I think, 4 astronomers in one room to get the microwave to make a periton. So it might be something like that.
That's less interesting than that. None, because they don't care about such short wavelengths.
I love it.
Thank you very much for joining us this evening, Emily. It's been great to have you at Astronomy Off Tap, not in Edinburgh, and great to hear such a fun story, and good luck with your research. Cheers.
Thanks very much.
Now, before we go on to our final talk of the evening, I'm just going to pass briefly back to John to flash up our game again for anyone who's still working on those acronyms. I understand someone has already solved it, which I'm frankly appalled by. I haven't solved it. John, do you have our game for us again?
I do. Thank you very much, Rachel. Amazingly, we had somebody solve it, I think within about 5 or 6 minutes from me sharing everything, which I have no idea how that works. It was some sort of, either somebody's time traveled, or they've got an amazing brain, or they've got some sort of secret program that I don't know about that undoes anagrams and creates words. So we had at Barbarette on Twitter, who posted up the answer, which was fantastic. I'll just share it one more time because I know a few people haven't got this yet. And if you aren't looking for spoilers, then stay off our Twitter feed so you can't see that. But I will post this up one more time just so everybody can see. So yeah, we actually had 2 people get it on Twitter, at Barbarette and at Becky E. Nesbitt, both posted up the correct answer. I won't ask them to show they're working, so don't worry. Nobody needs to sort of show the different words that they got. I will show everything at the very end of today's event, so don't worry. I'll make sure everybody has all of the answers. But yeah, so if you do want them and you don't want to see them, you can. It is on Twitter. You can kind of skip past and sort of hold a hand over your eyes where you're not looking at the answers. But it is on Twitter as an image, so you can look at it there as well. So if anybody else or anybody in the team or any of our speakers are able to figure this out as well, please do post it up either on the YouTube chat, on Twitter, on Facebook, and we'll give you a shout out. We don't, as I said, we don't have any particular prizes, and obviously we're not going to trace you because of GDPR implications, but we will try and sort of give you a shout out on Twitter or Facebook because the 2 people who got it did fantastically well to get it. I thought this was really hard, apparently not. So I'll again, it's up on our Twitter page if you want to have a look, and I will share the answers at the very end as well. There we go.
Oh, I feel thoroughly shamed. I've managed to solve 3 of them. So that is pretty embarrassing. On to our final talk of the evening, which is Ashley Pagnotta, who grew up in a suburb outside Houston, Texas, and did her undergrad work at Texas A&M in maths and physics, and then moved 1 state and an entire culture away to do graduate work at Louisiana State University, studying various explosive transient phenomena. After finishing her PhD, she spent 5 years doing a postdoc at the American Museum of Natural History in New York City, which is where I met her, where unfortunately the dinosaurs do not come alive at night, she says. That's extremely disappointing. She's now an assistant professor at the College of Charleston in South Carolina, teaching physics and astronomy and continuing her research with a small group of undergrads. She loves proper observing at the telescope, as well as talking about science to all audiences, from middle school students to the general public to other researchers. In her elusive spare time, she enjoys knitting, live music, podcasts, photography, cooking and baking, hiking, watching TV, although not all at once. She's also attempted to teach me to knit, which went questionably. So welcome to Ashley.
Hello. Yes, thank you very much to Astronomy on Tap Edinburgh for having me virtually. I do have to give a shout out to my Scottish heritage. I come by the red hair naturally, and I was going to wear my tartan scarf. So my family's from the Moffat clan. So if you start in Edinburgh and drive about an hour and a half south, you'll get to a tiny little town of Moffat, Scotland. So I was going to wear my tartan scarf, but I'm now in South Carolina and it's August. So wool scarves, not really a great thing to be wearing. So let's go ahead. Let me go ahead and get this up. Hopefully y'all can see this now. So I am going to give a talk called Improbably High and Almost Certainly Not Real. So what does that mean and where did I come up with that? So if you stick around to the end, I promise you will find out. The main subject of my talk today is a woman named Cecilia Payne Gaposchkin. So I'm actually going to mostly refer to her as Cecilia Payne because most of the work that I heard you're seeing presenter view. Let me swap displays. Hopefully you are seeing the full slides now. Okay, so Cecilia Payne, again, so I'm mostly going to refer to her as Cecilia Payne because that is what that was her name during all of the work that I'm going to talk about today. So she got married later on to a man named Sergei Kapashkin and then took his name, but started off as Cecilia Payne. She was born in England in 1900 and she went to Cambridge. So on this side, you'll notice I don't say that she graduated from Cambridge. She finished at Cambridge in 1923. And the reason that I say that is because she did not actually get a degree from Cambridge. So she did all of the coursework, all of the requirements for a degree in physics and chemistry. But because she was a woman, she was not granted a degree. Cambridge did not grant degrees to women until much later on, a couple decades later. So she did all the work, but she didn't get the fancy piece of paper. But she moved to the US, to Cambridge, Massachusetts. So from Cambridge, England to Cambridge, Massachusetts, to work at the Harvard College Observatory in 1923. So I'll take a brief detour and talk a little bit about the Harvard Observatory. So by that time, there was a well-established group of women working at Harvard. This is a picture of a bunch of the women, and you can kind of see the working conditions, see what they were doing. So what they were doing is they were looking at glass plates. So nowadays, and we heard all about this before, basically we take digital pictures of the sky. So we have essentially fancy digital cameras with sometimes 13 pixels, sometimes a lot more. And we take those the same way that we would the digital pictures that we take with our phones or with a digital camera. Back in the day, pre-digital cameras, so when we took photos with film, we basically did the same thing at the telescope, except instead of a flexible film, we used a glass plate, so a sheet of glass with a photo emulsion on one side. And you slide that into a contraption on the end of the telescope, expose that the same way you would expose a film photograph, and then you can use that later. So it goes through a similar type of development process, and you can use that later to look at those pictures of the sky. So Harvard started taking those pictures in the late 1800s, and starting in 1881, it was predominantly and then exclusively women working with those glass plates. So the fun, possibly apocryphal story about this is that the director of the observatory at the time, Edward Pickering, he got really frustrated with the men who were working there, and he sort of had a fit and said, you know what, my maid could do a better job than you could. And he hired her, a Scottish woman named Wilhelmina Fleming, and she did do a better job. And so after that, he only hired women. So we have this group of women known as the Harvard computers, because they were computing things by hand, looking at these glass plates, computing things by hand. And you can see kind of in the background of this image, you can see there's a light curve. You see some type of dip in the light curve. And they were looking at the brightnesses of stars, and they were also looking at the spectra. So Jeff gave us a great intro of spectra. We'll see some more of those later. So that is sort of setting the stage. So in 1923, Cecilia Payne moves to Massachusetts to start working at Harvard, to start doing astronomy at Harvard. So at the same time, that same year, Niels Bohr published his model showing how you have, so what we now call the Bohr model of the atom, where you have these orbits containing the electrons that are in orbit around the nucleus of the atom. So you have the nucleus of the atom, that's where the protons and the neutrons are. You have electron and electron in orbit around that nucleus. And there are different levels that electron can be at. So you have a ground level, and then you have higher levels that correspond to higher energies. So if you have an electron that either jumps up from a lower level to a higher level, or jumps down from a higher level to a lower level, you either have to absorb some energy or you will release energy. So if you're going from low to high, you absorb energy. If you're going from high to low, you release energy. And we see this in the spectra. So if you're absorbing energy, we see that absorption spectrum. And if you are releasing energy, we see what we call an emission spectrum. So this is a sample spectrum of the element calcium. So you can use these spectra, like Jeff was talking about, to kind of get an idea of what the object you're looking at, whatever's producing that light, is made up of. So in this case, what are its stars made up of? So around the same time, Saha related what we call the ionization state of an element to the temperature and pressure of that element. So here we have hydrogen, helium, lithium. These are our standard first three elements on the periodic table. Hydrogen usually has 1 electron. Helium has 2 protons, 2 electrons. Lithium, 3 protons, 3 electrons. These are in their normal unionized state. But depending on the temperature and pressure, they can become what we call ionized. And so in that case, usually you end up losing an electron. So you would have a hydrogen ion, which would have still the single proton in the center, but no electron, or a helium ion, singly ionized helium. So it has still the 2 protons in the center and only 1 electron. Similar for all of the other elements. You can ionize them, you can multiply ionize, there's all this kind of stuff. So a key takeaway from this is that the spectrum of an ionized element looks different from the spectrum of the neutral element, the unionized one. So again, if you have your neutral helium versus your ionized helium, the spectra that you see are going to look different. Okay, so how does this all relate back to Cecilia Payne? So she actually looked at these spectra. So she took a sample of about 100 stars. This is work she was doing right after she got to Harvard. She took a sample of 100 stars, looked at their spectra to see what she could find. So this is in particular for the astronomers who are used to looking at spectra taken with CCDs and high resolution diffraction grating. So these are some sample spectroscopic plates from Harvard. You can see here we have 2 different resolutions. So these are they're rotated. In this case, on the left, the spectra, you can see they've been stretched out vertically. On the right, they've been stretched out horizontally. It's the same basic idea like we saw before. Light goes through the prism, it gets stretched out into its different wavelengths. So on the left, they haven't been stretched very much. It's a very low resolution spectrum. On the right, it's a little higher resolution. And if you are looking closely and you're familiar with the Harvard computers, you might notice on this plate on the right, you see AJC. See those initials next to a bunch of these spectra. So that is, in fact, you might be thinking anti-jump cannon. That is anti-jump cannon. These are some of the spectra that she looked at. But let's look at an even sort of more higher res spectrum. So this is zoomed in and blown up. On the plate, it was about maybe 10 centimeters long. So it's fairly stretched out compared to those other ones. I should say the scale on these, so they're 8 inches by 10 inches, and that is not a conversion I'm gonna do in my head really quickly. Shorter than an A4 piece of paper, about the same width, a little bit shorter for the non-Americans watching this stream. But so here's a slightly higher res one. And so you can see some of these lines look like really relatively easy to see. They're pretty bright. But then some of them, so all of the markings that are written along the top, those are marking spectral lines. And a lot of those you look and think, ooh, I don't see anything there. And so this just kind of tells you how good these women were at working with these plates, seeing these lines, seeing very small variations in brightness. They were really very talented and very good at what they were doing. So Cecilia looked at a sample of 100 stars, looked at spectra like these, and again was looking for the differences in the lines that she was seeing. Was she seeing hydrogen? Was she seeing helium? Was she seeing ionized hydrogen, ionized helium, all this kind of stuff? So you can plot out the relative line strength of different types of lines, so ionized helium, neutral helium, etc. And what we have plotted on the x-axis, so what's labeled here is what we call the spectral class, OBA-FGKM. That was developed by Annie Jump Cannon, who I mentioned previously. But what this also corresponds to is the temperature. So hotter stars are to the left, cooler stars are to the right. And so you see that when it's very hot, you get strong ionized helium, and then as it cools down, you see your neutral helium, hydrogen, and so forth. So this is an excerpt from Cecilia Payne's 1925 PhD thesis. And the key takeaway from this is that once you know the temperatures, you can calculate the abundances of each of the elements that are in that star, that you see in that spectrum that are in that star. And so this is sort of the key equation. It's okay if you don't understand what's going on here. Again, the most important thing is that given the temperature, you can calculate N sub R, which is the abundance, the proportion of each of the different elements that are part of that star. So this is her table, table 5. We can look and see, so we've got atomic number, atom, relative stellar abundance. So she's looking, again, at these 100 stars, and then the terrestrial abundance. So how does this compare to what we see on Earth? And so you see silicon is pretty high, not as high as it is on Earth. Sodium is pretty high. Magnesium, aluminum, carbon, calcium, all the way down. So lithium, there's almost no lithium. Tiny little bits of barium, strontium, etc. All these things that when Jeff was talking about this idea that we are star stuff, we are made up of the things that were created in stars, all of these different elements. But you might have noticed there are 2 big omissions from this table. So all of these common elements, most of which you've probably heard of before, but there's 2 elements that you don't see. And so those 2 elements, if we were live, I would make you, or if we were in person, I would make you shout them out. And I'm sure somebody is yelling at their computer right now, hopefully. The 2 elements are hydrogen and helium. And so the text directly underneath this table says that hydrogen and helium are omitted from the table. The stellar abundance deduced for these elements is improbably high and is almost certainly not real. So what Cecilia found was that the vast, vast majority of all of the stuff in stars was hydrogen and helium, and really mostly hydrogen, a decent chunk of helium, and then if you look, maybe like 15, getting close to 20% other stuff, but almost exclusively, almost entirely hydrogen and helium. And especially when you look at specific types of stars, you see even greater of a percentage of hydrogen and helium. So why did she do this? Why did she omit these from the table? Why did she say, oh no, that's probably not right? So again, kind of relating back to the last talk of like trying to understand what was going on. They didn't really understand why they would be that high. And in particular, so she, as she tells it, this is all from her autobiography, as she tells it, she was confident in her results. She knew that they were correct. She wanted to include them, but one of the people sort of advising her thesis was Henry Norris Russell. And if the name Russell sounds familiar, maybe from the Hertzsprung-Russell diagram, and he basically read her thesis draft and he came back and said, no, this is wrong. This can't be right. this doesn't match up with what we think should be true. So you need to put a sentence in here that says, whatever I got, it's wrong. Don't believe it. Something must be wrong with it. And so she did. Sometimes you have to make concessions for your PhD committee. And then a couple of years later, Russell discovered this same thing over again in a different way. And then he published it and was like, oh yeah, by the way, stars are mostly hydrogen and helium. He did cite Cecilia Payne's work, but he didn't ever acknowledge the fact that he had strongly encouraged her to put this negating statement in. So again, from her autobiography, I just really love this quote. She says, I had given in to authority when I believed I was right. That is another example of how not to do research. I note it here as a warning to the young. If you are sure of your facts, you should defend your position. I highly recommend her autobiography. She is quite a pistol. It's a pretty enjoyable read. Speaking of, so this is here on the left. If this kind of stuff is interesting to you, if you're interested in the Harvard computers, Davis Sobel has written a really great book called The Glass Universe. And then there's also a really neat citizen science program happening called Project Phaedra. So I said that Cecilia and all these other women were working at the Harvard College Archives or Harvard College Observatory with the glass plates. So in total, there are about 500,000 glass plates, and there are also corresponding logbooks. So even to this day, when we go to the telescope, we keep a log of what's happening, like earlier saying, hey, can you check the logs on what was going on these days? Like, was there any interference happening? So same kind of thing. Were there clouds? Was the telescope being weird? So there's all these incredible logbooks. And the Project Phaedra project is looking to work on getting transcriptions of all of those logbooks digitally. So they're all handwritten, of course, because they, from the 1880s onward, and getting them digitized and then being able to match up the information that's in the logbooks with the information that's on the plates. So there are telescope logbooks. There are also the logbooks that the women kept as they were working, doing their calculations, doing their computing. So if you're interested in that, those are two really cool things. But yeah, so that's the story of Cecilia Payne. She went on to be the first woman to get a PhD. Well, she went on to get her PhD from Harvard. She was the first woman to be I think she was the first woman to get a PhD there. I should know this. But she was definitely the first woman to be the head of the department. So she became the chair of the astronomy department in the observatory, and she was the first woman at Harvard to do that. So she's pretty cool. She went on to also study exploding stars and did a lot of other interesting stuff. So that's Cecilia Payne.
Wow, thank you so much for sharing that with us, Ashley. It's a really interesting story. And I think interesting contrast with Adam Rees, one of the Nobel Prize recipients that Jeff referenced in the first talk tonight, who similarly made a really unusual kind of groundbreaking discovery when he was like pretty freshly minted PhD when that came out, but got taken seriously, whereas Cecilia's absolutely right work was hidden away.
I wonder why.
Can't imagine. So some questions. You mentioned Cecilia's thesis. Does that mean she graduated with a PhD, so she's a doctor, but she didn't officially have an undergrad?
Yes, that is correct.
That's
I don't know if that would happen anymore. I don't know if you could get into grad school without an undergrad degree.
And so for the other Harvard computers, were they, what was their backgrounds? Do you know, were they graduates from anywhere or just really smart women like in the movie Hidden Figures?
All of the above. Some of them, a lot of them sort of funneled through Barnard. So when Harvard was kind of male only and Barnard was the women's college. No, is it Barnard? That's the one that's with Columbia. What's the one that's with Harvard. Oh, I don't know. Whatever the women's college associated with Harvard was, a lot of them sort of went there to study and then came to Harvard, or there were women who went to, they might have been up at like what we now call Maria Mitchell Observatory in Nantucket, or had been, involved in sort of local astronomy type stuff, and then ended up sort of wanting to take it to the next level, and were able to get hired at Harvard. So initially it was just kind of hiring women who were smart and meticulous and were, good at doing, yes, thank you, Erica, it's Radcliffe. So Radcliffe College is the women's college associated with Harvard. But sort of smart, meticulous, just very like good and careful with their math. But then it did end up being also a number of women, sort of as as it became sort of, it was, for a while, it was like the only place to work if you were a woman astronomer and wanted to have a job doing research. That was basically the only observatory that had, a group of women working there that you would work at, because there were still, the women were not allowed to go to the telescope. They were not allowed to actually observe at the telescope. That was considered to be too dangerous, too scandalous, but they could work with the data. So that was something.
I mean, of the logs from that time, how many of them have been digitized so far?
I have no idea. You'd have to go to the Project Phaedra website. Some of them, I think a lot of the sort of the big names, I think a lot of Henriettas have been digitized. So Henrietta Leavitt was one of the more well-known computers. I think a bunch of the folks who have, the women who sort of show up in the Glass universe, who are these sort of bigger names, a lot of their logbooks have been digitized, but I know there are a bunch more still. I don't know the percentages though. I'm sure the Project Phaedra website has all that information.
And are they still useful for research today?
They are. I actually use the plates for research all the time. So one of the sort of trendy things in astronomy right now is what we call time domain astronomy. We want to know not just what our stars, galaxies, et cetera, are doing right now at this minute, but what were they doing before? What were they doing 10 years ago, 20 years ago, 100 years ago? And so for the past 30, 40 years, we have digital data, we have CCD data and photometer data. But before then, if you want to know what your star was doing 100 years ago, the plates are the only source of that information. And so I actually used the plates both in person, so you can go to Harvard and look at the plates in person, but they also have this scanning project going on called DASH, DASCH, and you can get access to scanned digital images of the plates through the DASH website. So they're still working on it. So there's not, you don't have access to the whole collection yet, but they've done a solid chunk of the sky and they are still going. And so eventually you'll have access to the whole sky digitally, which is a pretty amazing thing. So it's about 100 years worth of data that is in the process of being digitized. And so if you want to know what did my star do between 1890 and 1980, that's one of the only places that you can go to find that out. And a lot of times, I mean, we do the same kind of thing of like, something looks weird on this plate or in this image. Maybe was there something going on? And you can go, it's amazing to have the logbooks available because you can go back and see, oh yeah, the tracking on the telescope was broken, or it was cloudy, so you can't, maybe necessarily compare the, the magnitudes, the brightnesses of the stars, like from one side of the plate to the other side of the plate, because there might've been a cloud, things like that. So it is really, it is a sort of like a treasure trove of information. It's not the easiest information to access. It takes a little bit of sort of extra extra learning and special training, but there's all kinds of cool stuff hidden in there. So.
Oh, and it's really cool that you can have data going back that far.
Right?
Last question for you. Why can you never trust atoms?
I don't know.
Because they make up everything. I'm very, very sorry. Thank you so much for joining us tonight, Ashley. That was a fascinating talk and a lovely bit of history of our field. So thank you very much.
Thank you for having me.
Now, before we go this evening, I'm going to throw back one more time to John, who is finally going to put us all out of our misery and tell us what is going on with those anagrams.
Thank you very much, Rachel. And thank you, Ashley, Emily, and Jeff for some fantastic, they're all brilliant talks. So thank you so much for your time and coming to join us on Astronomy Off Tap. So yeah, we've only still had two people solving my little riddle today, which is very impressive. And also, you know, terribly for AOT. I don't think that we've had anybody from the team who's quite figured it out yet. So I will just share with you now my screen so everybody can see. So we had all of our different words on our screen, and I'll show you these through the magic of PowerPoint, each one at a time. Our first one, as I just put my helmet on, was of course light year, which gives us our L. Our second word was Europe. That was the easiest one. If you didn't get Uranus, then you know, it's terrible. I don't think you can't forgive yourself for that. So that gives us our U. Then of course we had Andromeda. That was tough. I'll give you that one, and that gives us our A. Neptune, that was an easier one, gives us our N. At this point, people should be, you know, alarm bells should be going off. We should be able to figure this one out. Exoplanet was a tougher one. Exoplanet was a difficult one. That gives us our E. And of course, finally, we had black hole, which gives us our B. So the answer was nebula. And if you got that, I did see that at Becky E. Nisbet did show her working on Twitter, so that was very impressive. But at Barbara was our number one. So if anybody else out there got it, well done. If you didn't get it, well, don't worry, it's no worries. We'll think up a more difficult game for our next AoT event. So well done for everybody for playing, and thank you for playing along, and congratulations to our two winners on Twitter. You did a great job. And I'll hand back to you, Rachel.
Oh, thank you very much for that. I got the 2 planets and black hole, and that is it. So that was pretty abysmal. So thank you so much again to all of our 3 speakers this evening. You're all marvelous. Thank you to everyone who joined us live and everyone who's checking in later. Hello from the past. If you have clear skies tonight, do try to get outside and see if you can spot some Perseid meteors. I'll leave you with one last really terrible joke. Why is a space rock tastier than an Earth rock? It's a little meteor. It's from a vegetarian. So if you enjoyed this evening, or if you would like to come back when I'm not hosting with my terrible jokes, you can find us again on the 8th of September right here on YouTube. We will have some more talks for you, some more astronomy and some more games and nerdy fun. Thank you so much for joining us this evening. Cheers.